হ্যালো, ঠিক আছে। হ্যাঁ আইডি তো সরি, মাইক্রোফোন লাগবে নিয়ে আসছি।
Dear audience, now we have with us Professor Dr. Mohammad Sajjad Hossain, who is the session chair of this session. So I'm just handing over the floor to Professor Sajjad Hossain. He will run the session.
Who are present here in our conference hall. We have a very important session today. Today, we are passing second day of our international conference on Fourth Industrial Revolution and beyond, organized by University Grants Commission of Bangladesh, to mark the birth centenary of our father of the nation and golden jubilee of independence of Bangladesh. This important session will be recorded video presented to the audience, our Nobel laureate, Professor Takaki Kazita, Nobel laureate in physics, 2015, recorded. The title of the topic is Neutrinos and Gravitational Waves. Professor Kazita Takaki, born 1959 in Japan, Japanese physicist who was awarded the 2015 Nobel Prize in Physics for discovering the oscillations of neutrinos from one flavor to another, which proved that those subatomic particles have mass. Kazita received a bachelor degree from Saitama University in 1981 and a doctorate from a University of Tokyo in 1986. That year, he became a research associate at the International Center of Elementary Particle Physics at UT. Kazita became a professor at the Institute of Cosmic Ray Research and director of the Research Center for Cosmic Neutrinos there in 1999. He became director of the institute in 2008. Ladies and gentlemen, and dear audience, let's listen this important recorded speech presentation of Professor Takaki Kazita, Nobel laureate in Physics 2015.
Hello everyone. Is the sound available?
Sojib, can you please share again? This is not audible.
Revolution and beyond.
Okay, can you hear now the sound?
Let me share.
Yes, please. Yes, please.
Okay, today I'm going to talk about neutrinos and gravitational waves. This is the outline of this talk. First, I'll briefly introduce my research history. Then I'll move on to the neutrino studies. I'm going to talk about Camiocandi, super Camiocandi, and future experiment hyper Camiocandi. Then I'll move on to the gravitational wave studies in Kagura. And I'll summarize this talk. And in fact, in the summary, instead of the usual summary, I'm going to talk about the role of basic research. Now, introduction. Here's my research history. I enrolled in the graduate course in 1981, and at that time, I joined the Camiocandi experiment, and this experiment continued until 1996. And after that, I moved to the super Camiocandi experiment. These experiments, Camiocandi and super Camiocandi, are neutrino experiments. And I actively worked in super Camiocandi until 2008. And then I moved on to the gravitational wave studies in Kagura. And in fact, for about 10 years, we have been constructing the Kagura interferometer. And recently, we finished the installation and we started the work toward the observation of the gravitational waves. So I'm going to talk about the neutrinos and gravitational waves. The first topic is the neutrino studies. And first of all, let me briefly discuss what are neutrinos. Neutrinos are fundamental particles like electrons and quarks. Neutrinos are something like electrons without electric charge. And this feature has a profound impact, and neutrinos can easily pass through even the Earth, but they can interact with matter very rarely. Therefore, we can study neutrinos. And neutrinos have, like the other particles, three types or three flavors, namely electron neutrinos, mu neutrinos, and tau neutrinos. And finally, neutrinos have been assumed to have no mass. Now, you may ask, how can we study neutrinos? Of course, we can never see neutrinos themselves. However, as I mentioned, neutrinos interact with matter. For example, a neutrino can interact with a nucleus. And if an interaction occurs, then a charged particle is typically emitted. And we have various ways to observe these charged particles. For example, in our case, we use water. Therefore, this charged particle propagates in the water. Therefore, these particles emit Cherenkov radiation or Cherenkov photons. And we observe these photons by photodetectors. And this way, we observe photons, therefore charged particle, and therefore this way we understand the neutrino interactions. Now, I move on to the Camiocandi experiment. The original name of Camiocandi was Kamioka nucleon decay experiment. Let me briefly mention the original motivation of the Camiocandi experiment. In the 1970s, ground unified theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. Of course, 10 to 30 years is a very long lifetime, but this number suggests that if we observe 10 to 30 protons for a year, one of them could decay. So we should be able to observe this long proton lifetime. So several proton decay experiments began in the early 80s, and one of them was Camiocandi. Here I show the sketch of the Camiocandi experiment. It is a large water detector. The water tank had about 16 meters in diameter and 16 meters in height. And this tank contained 3,000 tons of very clean water. And inside the tank, we installed the photodetectors. And if a proton inside this tank decay, then typically 2 to 3 particles will be emitted. And these particles propagate in the water and therefore emit Cherenkov radiation. And these radiations should be observed by these photomultiplier tubes or photodetectors. And this way, we wanted to observe proton decays. Unfortunately, oh, sorry, I want to show you this slide. This is the, this shows the location of the Camiocandi experiment. And you see the Camiocandi detector was located in the Mount area in Japan. And I also want to show this photo. This photo was taken during the construction of the Camiocandi experiment. And you see Professor Koshiba in the middle. And Professor Koshiba was the leader of the Camiocandi experiment. And indeed, he received Nobel Prize in Physics in 2002 based on his neutrino studies in Camiocandi. And this is the photo of the Camiocandi experiment. And the photo was taken at the end of the construction. You see already the tank was filled with water. And also you see photomultiplier tubes inside the water tank. And the experiment started in July 1983. Unfortunately, we didn't observe proton decays. However, we realized that the photomultiplier tube developed for Camiocandi had a very good sensitivity. This is the photo of the photomultiplier tube used in Camiocandi. It had a 50 centimeter diameter. Then Professor Koshiba realized that boron H solar neutrinos could be observed. Let me mention the reason for Professor Koshiba to propose solar neutrinos. In the early 80s, people knew the missing solar neutrino problem. And many people thought that the problem must be due to some problems in either the solar model or in the experiment. Therefore, he thought that Camiocandi could contribute to understand this problem by having another experiment to observe solar neutrinos. So he proposed to improve the Camiocandi detector to observe solar neutrinos. Well, certainly we moved on to the solar neutrino observation in Camiocandi. It took us several years to improve the detector. And we started the experiment in January 87 with the low threshold to be able to observe solar neutrinos. Then something unexpected happened in February 1987. Here I show the photo of the Large Magellanic Cloud. And this is before the supernova explosion, and this is after. And you see clearly after the explosion, you find a very bright star in Large Magellanic Cloud. As I said, at that time, Camiocandi was in the observation of the low-energy solar neutrinos. And therefore, we looked at the data and we found that Camiocandi recorded 11 neutrino events within 13 seconds. Also at that time, IMB3 experiment and the Baxan experiment observed neutrino events from supernova 1987-8. So, in total, there were 24 neutrino events. With these events, we understood the basic mechanism of the supernova explosion. And for this achievement, Professor Koshiba received Nobel Prize in Physics in 2002. Now, I said that the original motivation for the Camiocandi experiment was the search for proton decays. As I said, unfortunately, we didn't observe proton decays. Instead, we observed neutrino backgrounds. And these neutrinos are created in the atmosphere of the Earth. Cosmic ray particles come into the atmosphere, then interact with the air nucleus. Then typically pions are produced. Of course, these pions are unstable and decay to a muon. And muon is also unstable and decay to an electron. And during this decay chain, neutrinos are created. And these neutrinos, most of them simply pass through the Earth. But sometimes these neutrinos interact in the Camiocandi detector. Anyway, in the 80s, we wanted to separate the proton decay signal and the neutrino background. Therefore, I developed a new software to improve the proton decay analysis. Then I accidentally noticed that the event rate of the atmospheric muon neutrinos was significantly lower than expected. Initially, I thought that this was my mistake. And of course, I tried to find out the mistake. And I worked for more than 1 year to find out the mistake. Unfortunately, or fortunately, we didn't find any mistake. Therefore, we decided to publish our data. So we wrote a paper. this was actually a simple paper. We simply reported the number of muon neutrino events observed. That was 85, and compared with the expected number based on the simulation, that was about 144. We also compared the number of electron neutrino events observed and expected. And for electron neutrinos, the observation and expectation agreed reasonably well. So we simply reported these data. Unfortunately, the world community was skeptical. However, I thought there must be something very important indicated in the data. So I was most excited with the data. On the other hand, we had no clear idea what was the cause of the deficit. Anyway, I enjoyed to find out the cause of the deficit, and I changed my research from proton decay searches to neutrino studies. Of course, we had no clear idea what was the cause of the deficit. However, from the beginning, we have been thinking that maybe the cause was due to neutrino oscillations. Well, neutrino oscillation was proposed by theorists Maki, Nakagawa, Sakata, and Pontecorvo. According to them, if neutrinos have mass, neutrinos change their type or flavor from one type to the other. For example, muon neutrino could oscillate to tau neutrinos. Here I show the oscillation probability. If a muon neutrino is created here and begin to propagate to the right, then at some point, the probability that muon neutrino to remain muon neutrino goes down. But if they continue to propagate, then at some point, the probability come back to unity. Then the probability go down, go up, and so on. And when muon neutrino disappeared, then tau neutrinos are appearing. So this is neutrino oscillations, and if this is the cause of the deficit, we thought that muon neutrino deficit can be naturally explained. However, there were other possibilities to explain the muon neutrino deficit. Therefore, we thought we needed to have more data to separate neutrino oscillations from the other possibilities. And for this, we thought this way. As I said, neutrinos are created in the atmosphere. Therefore, some of them are created above us, typically 10 to 20 kilometers above us. And these neutrinos come to the detector after traveling only 10 to 20 kilometers. Therefore, these neutrinos may not have enough time to oscillate. On the other hand, neutrinos are created in the other side of the Earth, and these neutrinos must propagate long distance, typically 10,000 kilometers, before reaching the Camiocandi detector. They have to propagate long distance, therefore they may have enough time to oscillate. And if this is observed, we thought this could be the evidence for neutrino oscillations. Unfortunately, Camiocandi was too small to observe this kind of up versus down asymmetry of the atmospheric muon neutrinos. We needed much larger detector, and that was Super Camiocandi. I want to move on to Super Camiocandi. And Super Camiocandi is a much larger version of the original Camiocandi detector. It is about 40 meters in diameter and 40 meters in height, containing 50,000 tons of very clean water. And this is an international collaboration. We have about 200 collaborators from 10 countries. And this is the Super Camiocandi detector. This photo was taken during the construction of the detector. And in Super Camiocandi, we worked very hard to observe, to understand the atomic neutrino problem. And in fact, we worked very hard, and in 2 years, we were able to show this data. Here, I show the zenith angle distribution, where cosine theta 1 means downgoing neutrinos, and -1 means upward-going neutrinos, and the data are for muon neutrinos. And these black dots show the data, and the hatched histogram shows the simulation. And clearly, you see for downgoing neutrinos, the data and simulation agreed quite well. However, for upward-going neutrinos coming from the other side of the Earth, the number of observed data was essentially half of the expectation. And this data can be easily understood if we assume neutrino oscillations, namely for neutrinos coming from the other side of the Earth. They oscillate, therefore, when they come to the Super Camiocandi detector, the probability that muon neutrino to remain muon neutrino is 1/2. So, this way, the world community was convinced that neutrinos oscillate. Now, I'd like to move on to the other problem, that was the solar neutrino problem. Of course, the sun generates energy by nuclear fusion processes, and during these processes, many neutrinos are generated. And the pioneering home-stake solar neutrino experiment observed solar neutrinos for the first time in the 1960s. However, the event rate was only about 1/3 of the prediction. And this problem was confirmed by the subsequent experiments in the 80s and 90s. Now, this problem was clearly understood to be due to neutrino oscillations by the data from the SNOW experiment and Super Camiocandi experiment. SNOW is a large heavy water detector. They use 1,000 tons of heavy water D2O. And by using the heavy water, SNOW experiment is observed the electron neutrino flux and the total neutrino flux, independent of the neutrino type. And the result is shown here. If SNOW observes the electron neutrino flux, then the event rate was about 1/3 of the expectation. But if SNOW observed the total neutrino flux, then the event rate was just as expected. And this clearly indicates that neutrinos, that electron neutrinos are only 1/3 of the total neutrino component from the sun. Since the sun can only generate electron neutrinos, therefore, this was clearly the evidence for solar neutrino oscillations. By the way, I would like to show the Super Camiocandi result, and the Super Camiocandi result is shown here. And Super Camiocandi is also sensitive to the total neutrino flux, but but super Camiocandi is most sensitive to electron-neutrino flux. Therefore, people realized that this observation is completely consistent with this null result. So this way, we found that solar neutrinos also oscillate. So by these observations, we understood that neutrinos have small mass. Now, I'd like to tell you why we are so excited with the small neutrino mass. And in order to convince you why we are excited, I'd like to show this plot. Here, I show the mass of charged leptons and quarks. There are 3 types of charged leptons, and the mass of them are shown by red colors. There are 6 types of quarks, and the mass of them are shown by blue and green colors. Now, I'd like to plot the neutrino mass. They are here. But to be honest, I still have to assume something, but without such details, neutrino mass are shown here. And clearly, you see the neutrino mass is much smaller than the mass of the other particles. And from this figure, you can read that the neutrino mass is approximately, or maybe more than, 10 orders of magnitude smaller than the corresponding mass of quarks and charged leptons. 10 orders of magnitude different. Very small. And we believe this is the key to better understand elementary particles and the universe. Therefore, we are excited. By the way, certainly, if we understand why neutrino mass is so small, we certainly understand the elementary particles better. But I also mentioned that small neutrino mass is important to understand the universe. Why? Well, let me tell you. Here, I showed the photo of the far universe. You see many stars and galaxies. Of course, we know that these stars and galaxies are made of matter. We know there's no antimatter star or antimatter galaxy. That is trivial. However, this is not understandable easily if we consider the history of the universe. We know the universe began with Big Bang. And in the Big Bang universe, the universe was extremely hot. And we naively expect that particles and antiparticles are always generated simultaneously. Therefore, in the Big Bang universe, we naively expect the number of matter particles and number of antimatter particles should have been equal. Then, with universe cooled down, matter particles and antimatter particles meet and annihilate. Therefore, we naively expect in the present-day universe, there should be no matter particles, no antimatter particles. But, of course, we know there are matter particles. Well, to be honest, we certainly understood the problem. We understood that in the Big Bang universe, number of matter particles was, say, 1 billion 1. On the other hand, number of antimatter particles was 1 billion. 1 billion 1 and 1 billion are almost equal. Then, with the universe cooled down, matter particles and antimatter particles meet and annihilate. Therefore, the present day universe have only one matter particle, that is this particle. So this way, we understand the matter particle problem. However, of course, we do not understand why there was extra one in matter particle side. On the other hand, many people think that neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. And if many people think so, then as science, we have to confirm the idea based on the experiment. Now, I'd like to briefly discuss the future direction, that is hyper-Camiocandi. As I said, we would like to understand the origin of the matter in the universe. And we'd like to observe if oscillation of neutrinos and those of antineutrinos are different. If this difference is observed, it will be the first step to understand the origin of the matter in the universe. For this, and the present day experiments are not powerful enough. Therefore, we are going to produce many neutrinos with the JPAC and Proton accelerator facility. And these produced neutrinos should be shooted to the new detector hyper-Camiocandi. And with this configuration, we'd like to observe the oscillation of neutrinos and those of antineutrinos are different. In fact, hyper-Camiocandi is a very large detector. It will be about 70 meters in height and 70 meters in diameter. The total mass to be used to the physics analysis will be about 10 times larger than super Camiocandi. So this will be really a very important experiment, and the construction already started in 2020, and the experiment will start in 2027. And of course, this is a very large international collaboration. We have more than 450 members from 19 countries. Now, I'd like to move on to gravitational waves. Well, gravitational waves were predicted in 1916 based on Einstein's theory of general relativity. And this is the image of the gravitational wave. In this image, two black holes make the binary system. And these two black holes orbit each other. And during this, in this system, the gravitational waves are generated. And finally, these two black holes merge, and a heavier black hole should be generated. Now, you may ask, what science we are going to do with the observation of gravitational waves? Well, at least we'd like to observe three kinds of gravitational waves. One is the merger of the binary black holes. And in fact, as I will explain shortly, many black hole mergers have been observed so far. However, we already realized that we do not understand the mass of these black holes. The mass of these black holes are rather heavy. So we'd like to understand how these black holes were created in the universe. The second target is the merger of binary neutron stars. And neutron stars are also compact and heavy stars. But with the observation of the merger of binary neutron stars, we'd like to understand the origin of the heavy metals in the universe. Of course, we know heavy metals such as gold, but we do not know how these heavy metals were generated in the universe. And finally, we'd like to observe supernova explosion. And by the observation of the supernova explosion with gravitational waves, we'd like to understand better how the heavy stars finish their life. So we think that the observation of the universe with gravitational waves is very important, very unique. Now, about 6 years ago, gravitational waves was observed for the first time. And this is the data recorded on September 14, 2015. And you see red curve and blue curve. And these are, in fact, two independent data from two independent interferometer located in United States. And the data told us that two black holes of 36 solar mass and 29 solar mass each merged at a distance of 1.3 billion light years, newly forming a 62 solar mass black hole. So this was really a great discovery. And a few years later, Nobel Prize in Physics was awarded to 3 scientists from the LIGO scientific collaboration. By the way, if you are careful, you notice that there is something strange. 36 plus 29 is 65. On the other hand, the mass of the black hole created was 62 solar mass. This means during this merger, 3 solar mass equivalent energy was converted to the energy of the gravitational waves. So, in a sense, this observation was the observation of the most violent phenomena we ever observed in the universe. Anyway, by now, there have been 19 gravitational wave events, and most of them are black hole mergers, but there are several black hole binary neutron star mergers and binary neutron star and black hole mergers. So clearly, we are now in the era of gravitational wave astronomy. So we'd like to join the gravitational wave astronomy. And we have been working hard in the Kagura project. Kagura is an international collaboration from 10 countries. We have about 400 members, and as you may see, Kagura is largely from the Asian countries. Kagura is a 3 kilometer by 3 kilometer interferometer. It is located underground to reduce the seismic noise. In addition, we are going to use cryogenic mirrors to reduce thermal noises. And here I'd like to show you the project history. Kagura project was approved in 2010. First thing we did was the excavation of the 3 kilometer by 3 kilometer tunnels. Then after the excavation, 3 kilometer by 3 kilometer beam tube was installed. These two photos were taken in March 2015 when we finished the installation of the beam tubes. As I said, we are going to use cryogenic mirrors, and this is one of them. This is a sapphire mirror whose diameter is 22 centimeters and the thickness is 15 centimeters. The weight of the mirror is 23 kilograms. Clearly, we need the world's best sapphire crystal. So this is one of them. Anyway, after the preparation work, we installed this mirror into the into the vacuum tank. And this photo was taken on November 30, 2017, when we installed the first cryogenic mirror into this cryostat. And this is one of the photos of the central area. And here's the beam splitter, and the beam is split into this direction and this direction. To this direction. No, maybe this direction, sorry. So anyway, you can see the system is quite complicated. And this complicated laser interferometer is controlled by a large computer system. This is the computer system to operate the Kagura interferometer. And this is the Kagura interferometer remote operating room. Of course, we cannot be inside the underground. We cannot be inside the underground site because any kind of human activity could cause a noise to the laser interferometer operation. So everything must be carried out remotely. And we have finished the installation of the interferometer in the spring of 2019. Since then, we have been trying to improve the performance by reducing noises. And here I show the history of the Kagura sensitivity. Of course, if we go down, that means that we have better sensitivity. So since August 2019 until March 2020, we have improved the sensitivity more than 3 orders of magnitude. And this is as design sensitivity. Anyway, after a very intense commissioning period, we started the operation in the spring of 2020, essentially with this sensitivity. Unfortunately, due to COVID-19, we stopped the operation in 2 weeks. And let me mention about the global gravitational wave network. The scientific output will be maximized by the global network. The next observation will start in late 2022, and Kagura will join the observation with reasonably good sensitivity. So we are working hard to join the global network in late 2022. And I'd like to tell you the merit to join Kagura to the gravitational wave network. And well, certainly, as gravitational wave astronomy, we would like to collaborate with optical astronomers. However, in order to collaborate with optical astronomers, we have to tell them the direction of the gravitational wave signal. Therefore, the determination of the source direction is very important. And this is the estimated accuracy for the determination of the source by LIGO and Virgo interferometers. LIGO is in United States and Virgo is in Europe. And if we have only these interferometers, then we find that for some directions, they have already achieved very good accuracy in the source determination. However, for many other locations, their source determination accuracy is not enough. Furthermore, there are even some directions that they are not sensitive. Therefore, we'd like to think about adding Kagura interferometer. And if Kagura joins to the gravitational wave network, then the accuracy of the source direction determination will be much improved. And therefore, we think that Kagura can contribute significantly to the gravitational wave astronomy. So we are working hard toward the next observation run. Okay, let me summarize this talk by mentioning the role of basic research. I think there is no doubt that the curiosity-driven basic researches are the base for the advancement of science. These scientific researches may not contribute directly to the economic growth. However, in many cases, science is the base for the technological development. Therefore, these basic researches should be encouraged. And in order to maximize the scientific output, we collaborate with many other countries. Furthermore, in order to get the best scientific results, we typically have to use or develop cutting-edge technologies which could contribute to the technology development. So we think that these international scientific collaborations will help develop good relations among countries. And finally, we think that science and the people who are trained in science should be one of the keys to develop technologies and eventually to develop countries.
Yes, sir.
Okay,
Yes, yes.
that's all from me. Thank you very much.
Dear
Okay,
audience,
Shraddha.
if you have
Could
any
you
question, please, send us. We will send this one to the Nobel laureate for possible answer. Thank you very much for joining us.
তোলেন ডামি দেই তা আপনি অনেক ছবি তুলছেন তা কিভাবে পাবো ছবিগুলো আমি ইউজিসি ডিরেক্টর আপনি স্যামসাং না আচ্ছা ঠিক আছে হ্যাঁ আপনার অনেক সুন্দর ছবি তুলছেন খুবই ভালো